260 minus 2%. Okay, so you're going to have to take 7% off of whatever you tested if you do that. So that's one of the problems. So it's nice if you're doing a first time thing to get the engine manufacturer to give you a calibrated engine. In fact, if you'll send them your induction system and your exhaust system, they will put it on the engine in the test stand and make it look, you know, as much like the airplane as it can. And then they'll give you a calibration and tell you exactly what kind of horsepower you'll get with a given set of conditions. And we'll talk more about that a little later. For stability and control, you don't want a lot of control system friction because it tends to mask everything. So, you know, you want the controls to be nice and free and not high in friction. And generally you would, in doing stability and control tests, you would actually measure the control system friction statically on the ground to determine what it is. Atmospheric conditions, avoid temperature inversions, which is where the temperature either becomes the same, you know, or changes. Well, you say in the wintertime, what you see usually is that takeoff is cold on the surface and you take off and it gets warmer as you climb to altitude. You're just wasting your time trying to get good performance data in those conditions. Wind shear. Again, these two are they're kind of tied together. If you've got a temperature inversion, you've probably got a wind shear there and it will mess up your data. Humidity. Here in Florida, we have lots of humidity. And that can be a big effect on your data. For instance, again, another experience, I was working at Rockwell in Albany, Georgia, and Albany, Georgia being on the south side of the state of Georgia is much like it is here in Florida. It's humid, particularly in the summertime. And so we were doing a test, doing a climb test, which set our gross weight, what was the maximum weight we could put in the airplane. And it turned out we were correcting for humidity. And if you read the FAA rules, the FAA rules said 1962 standard atmosphere assumed dry air. Well, the air was not dry. And so we were correcting for that by sticking a wet and a dry bulb thermometer out the vent window and getting and going back in and determining the pressure, partial pressure of water vapor, and then taking that off of our manifold pressure, which we were determining power from. FAA says, no, we're not going to allow you to do that. If you correct for humidity, you got to correct back to 80% relative humidity. Well, it turned out that that's what we did anyway, was correct back. But we said, we don't think that's fair because people out in Wichita don't have these conditions and we're competing with them. And they said, we don't care, you can go someplace else and test, but if you're going to correct for humidity, you're going to correct 80%. So we said, fine, we're going to Mojave. We flew the airplane out to Mojave and got a 100-pound increase in gross weight on a 2,500-pound airplane, okay? A 100-pound increase in gross weight by not correcting for humidity and testing in a dry climate. No change to the airplane whatsoever, just that. So that's the kind of thing. And what happens when you plot up the rates of climb, say this is rate of climb, you know, and this is, no, I'm sorry, this is altitude, not rate of climb. This is altitude, H and P, and this is rate of climb. What happens is that in dry air, your data points will look something like this as you go to altitude in dry air. ground, so you extrapolate that to sea level, and that's where the requirement is at sea level. If you test at high humidity, what you'll find is these last 2 points here at low altitude will come down, and then you have to fare the curve like that. And you lose that much sea level rate of climb due to that. And as a result, you can't get as high a gross weight increase. And most of the humidity is close to the surface of the earth. It isn't at high altitude, you know, and the high altitude points will all be about the same. And that's the effect of humidity that you have to be careful of. Turbulence, well, you don't want to ever test in turbulence. You know, the lawyers will tell you, oh, well, you didn't test in turbulence. Well, you can't get any decent data in turbulence. So how do we avoid these things? Well, I've already talked to you about using the side of the hysteresis band, which applies to what data you're getting. Sample size, well, you know, we'd like to get all the data we can get, but you gotta reach some happy medium, so you try to do that to minimize them. Reading errors, select larger scales on the instruments if you can. Read instruments from directly in front of them if your hand is recording. Read the most important parameters first. We're going to be doing a lot of things in here. We're going to be hand recording the data. You'll be writing it down on a data sheet, okay? And if we're doing something, determine which of the important parameters. I'll try to tell you that, and we will do that. We'll be done in just a minute, folks.
Great, thank you.
Temperature inversions, we talked about that. Perform climbs descent at right angles to the wind. We'll talk more about that when we do that. And use opposite headings for climb and descent data. We'll talk about why. High humidity, we've already mentioned. Adequate time to trim and stabilize. Good idea to approach a airspeed point from a higher airspeed where you can. And make yourself a checklist from well, a lot of mathematical techniques don't apply to flight tests because the sources of error can't be quantified. I use what I call a common sense approach. It ought to be smooth and consistent. There shouldn't be large discontinuities. Test the results against the theory. The curve ought to look like the theory. Does it correlate with other data? Does it correlate pilot to pilot? Does it correlate test method to test method? And then you can use some curve fits. And by the way, curve fit on your computer on Excel is least squares. Least squares takes every data point into the same account. Weighted least squares where if you see a data point that's way out, that doesn't, you can say, now we're going to give that a zero weight and ignore it. There's a better approach for flight testing. Okay, questions? Yes, sir.
We're going to have